There's a lie we all believe about infrastructure, that once it's built, the only way to change it is to tear it down. Wrong. Engineers have been quietly ignoring that rule for 70 years. They slice ships in half. They pick up bridges and walk them across rivers. This is how they actually do it. The problem is math. A 1,000-foot cargo ship costs about $1 billion to build. A new highway bridge can cost $200 million, and they take years. But the world doesn't wait for you to catch up. Cargo volumes grow. Traffic counts climb. You need more ship, or more bridge, and you need it now. So what do you actually do? Here's the part most people don't know. This isn't a modern trick. This started right after World War II. The U.S. had built thousands of T-2 tankers during the war, 523 feet long, workhorses of the Allied supply chain. By the late 1950s, they were aging out. Too small for the new oil markets, too small for post-war shipping volumes. So in 1959, at American Bridge in Orange, Texas, two of those tankers, the Four Lakes and the Cabinda, got sliced in half. New midsections welded in. They came out 49 feet longer, 22% more cargo capacity. Same hull, same engines, same crew. The economics were undeniable, and the technique never went away. Two completely different industries, shipping, highway construction. They arrived at the same answer. Don't build a new one. Modify the one you already have. In the shipyard, they cut ships in half and add a new middle. On the highway, they build the entire bridge somewhere else, then walk it into place, overnight. This is how. It's called jumboization, and the name makes it sound cute. It isn't. Shipyards take a fully finished ocean-going vessel, a cruise ship, a cargo ship, a tanker. They drag it into a dry dock, and they slice through the hull. Clean, vertical, from waterline to keel. The whole ship, split in two. Here is what the cut actually severs. Hydraulic lines, fuel lines, sewage lines, fresh water pipes, HVAC ducts, fiber optic cables, power cables, structural steel frames, load-bearing bulkheads, navigation wiring, fire suppression systems. Every single one of those has to be cut cleanly, labeled, capped, and eventually rejoined. If you miss one, just one, the ship either sinks or catches fire, or both. The people doing the welding are not normal welders. They're called Lloyd's Coded Welders, or ABS Certified Welders, Lloyd's Register. 1760 British Classification Society, American Bureau of Shipping, both publish a rulebook called the Materials and Welding Code. To work on a hull bisection, a welder has to pass a qualification test. Their welds are X-rayed, mechanically pull-tested, witnessed by a third-party surveyor, logged, stamped, traceable to the individual, and recertified every 2 years. Because if a coded welder's seam fails, they don't just lose the job, they lose the certification, which means they don't work in shipbuilding again. The welder who closes the seam on a billion-dollar ship has more on the line than the project manager. While the existing ship is being cut, a brand new middle section is being built. Somewhere else, in a different shipyard, maybe a different country. It arrives by barge, or by heavy lift ship, or in some cases, they build it right alongside, in the same dry dock. This section is complete. Steel, wiring, piping, furniture, sometimes entire hotel floors, full, ready to run. And it weighs, often more than 1,000 tons. And here is the part they don't advertise. Those two halves of the existing ship, they're no longer one structure. They have maybe half the lateral rigidity they had yesterday. A sudden gust of wind, even a stiff one, has enough kinetic energy to topple either half. Crews watch the weather, obsessively. A cut that goes bad on a windy day ends with a destabilized hull tipped into the dry dock floor. Millions in damage, in seconds. When the new midsection is welded in, the real test begins. Every pipe that was severed has to be rejoined. Waterproof. Every fuel line, every sewage run, every hydraulic circuit. The welds have to be certified, the pipes pressure tested. Because the ship is about to be undry docked. The dock gets flooded, the water rushes in, and if one of those thousands of new joints leaks, the ship sinks. Right there, at the dock. But when it works, when the welds hold, when the power comes back online, when the dock floods and the ship floats, what you have is a longer ship. More cabins, more cargo capacity, more revenue per voyage. for about $80 million. A new ship would have cost more than $1 billion and would have taken 4 years to build. This one took a couple of months. That's the entire economic argument for jumboization. In one sentence, if you want to understand how serious this technique can get, look at the Seawise Giant, the longest self-propelled ship in human history, originally built in 1979, already enormous at 1,235 feet. Then, in 1980, they cut it in half. They added a midsection, 81.8 meters long, 268 feet, of new ship. Welded in, the result, 1,504 feet stem to stern, 458 meters. To put that in perspective, the Empire State Building tipped on its side is shorter. The deadweight tonnage went from 418,000 tons to 564,000. The biggest movable object humans had ever built, made bigger by cutting it in half. Since 1977, at least 21 major cruise ships have been jumboized. The Silver Sea Silver Spirit, the MSC Magnifica family, the Costa lines, even Norwegian cruise line ships. The reason is the same every time. A new cruise ship costs roughly $1 billion. A jumboization costs about $80 million, 12 times cheaper. The new midsection arrives, already furnished, already cabined, already plumbed. They literally float in a hotel section. Weld it to your ship. Open the doors to paying passengers within 90 days. The math is so good, you'd be a fool not to do it. Now leave the water. Same problem, different world. A highway bridge, 4 lanes, 50 years old. Concrete spalling, rebar corroding. It needs to be replaced. But it's carrying 27,000 cars a day. You cannot close that road. Not for a year, not for a month, barely for a weekend. So how do you replace an entire bridge without closing the road? In 2004, the U.S. Federal Highway Administration ran an international scan. They sent engineers to Europe, to Japan, to find a way out of the problem. They came back with a single top recommendation: build the bridge somewhere else, then move the whole thing into place. All at once. They called it Accelerated Bridge Construction, ABC. And the machine that made it possible wasn't a crane. It was a platform on wheels. Before we get to what an SPMT does, here's where it came from. 1983, 2 companies, Mammoet, a Dutch heavy lift firm whose roots go back to 1807. They moved cargo on Amsterdam canals before there were highways. And Scheuerle, a German trailer manufacturer. They sat down together and asked one question: could we build a transport platform that solves all the heavy lift problems at once? Modular, self-propelled, with computer-controlled steering. The North Sea oil boom was driving demand. Massive offshore platforms had to be built on land, then moved into the water. Cranes alone couldn't do it. So in 1983, Mammoet and Scheuerle delivered the first SPMT. 43 years later, every major heavy lift on Earth uses the same basic concept they invented. An SPMT, a self-propelled modular transporter. And the words matter. Self-propelled, it has its own engine. Modular, you can connect them together, like Legos, head to tail, side by side, until you have a deck big enough to hold whatever you're moving. Transporter, it moves, but how it moves is where this gets weird. Where does the power come from? An SPMT module by itself has no engine. The engine sits in a separate box, called a power pack unit, PPU, about the size of a shipping container. Diesel, 500 to 800 horsepower. It connects to the SPMT modules through high-pressure hydraulic hoses. One PPU drives multiple modules. The hydraulics turn every wheel, every steering joint, every axle cylinder. The PPU is the heart. The SPMT is the body. And here's the elegant part. If you need more power, you just plug in another PPU, modular all the way down. Here is the part that breaks your brain. On a normal car, the 2 front wheels turn together. On an SPMT, every single wheel pair turns on its own axis. Computer-controlled, 360 degrees, which means the platform can do 4 different things. It can drive forward. That's normal steering. It can drive sideways, without turning the deck. That's called crab steering. It can pivot in place like a record player. Carousel steering. Or it can crab diagonal. All at once. This is how you get a 100-foot bridge through a 12-foot gap. Each axle also has its own hydraulic cylinder. which means every single wheel can go up or down independently. About 60 centimeters of travel, 2 feet, which sounds small, until you realize what it lets you do. It lets the platform absorb the road. A pothole under one wheel. That wheel drops. The platform stays perfectly level. And when you're carrying a 1,000-ton bridge on top, level matters. Because if the deck tilts even 1 degree, the bridge twists, and twisted concrete cracks. One more thing about how this machine actually behaves. An SPMT does not race. It moves at walking speed, roughly 2 to 5 kilometers per hour, about 1 to 3 miles per hour, on purpose. Because when you're carrying a 1,000-ton load, acceleration becomes your enemy. Inertia is the killer. Brake too hard. The cargo pitches. Tilt happens. Concrete cracks. So the operator doesn't drive it like a truck. They drive it like a ballet. Tiny inputs. Slow corrections. The platform accelerates over minutes. Decelerates over minutes. A move of 300 meters can take 6 hours. The bridge has all the time in the world. Put all of that together, and here is what you can do. Build the new bridge in a staging area. Months of work. Away from the highway. Nobody on the live road. Nobody under traffic. Workers in safety. Then on a Friday night, you close the road. You roll the OLD bridge out. You roll the new bridge in. You drop it onto the abutments. You open the road Monday morning. That's not fantasy. That's the standard FHWA Accelerated Bridge Construction Playbook. Case 1. Pittsburgh, 2019. The Scheuerle Street Bridge. A 2-span steel beam bridge over U.S. Route 19. 140 feet long. 27,000 cars a day rolling under it. Primary route from downtown Pittsburgh to the airport. PennDOT, the Pennsylvania Department of Transportation, had never used an SPMT before. Not once. This was their first. The Federal Highway Administration gave them a $400,000 grant to try it. 2 weekend closures, instead of a year of corridor shutdown. That's the whole story. SPMTs are not the only way to do this. There's a second method. The Federal Highway Administration calls it Slide-In Bridge Construction, SIBC. The lateral slide. You build the new bridge directly next to the old one, same elevation, on temporary supports. Then you hydraulic jack the old bridge sideways out of the way, and you slide the new bridge sideways into position, on Teflon pads, hydraulic jacks pushing it horizontally. 6 U.S. states have made this their primary method. Utah, Oregon, Colorado, Missouri, Massachusetts, New York. Why pick this over SPMTs? Sometimes the bridge is too long to truck through city streets to a staging area. Sometimes there's no staging area at all. The lateral slide solves both problems. The bridge is born exactly where it dies. Case 2. Leverkusen, Germany, the Rhine River. Engineers needed to replace a section of a major Autobahn bridge, 66 meters long, 34 meters wide. Weight, 1,100 tons. But the abutments on either side were at different heights, and the bridge deck had a slope in 2 directions at once. Longitudinal slope, transverse slope. You cannot stack a bridge like that with conventional jacks. Physics won't let you. A company called Mammoet brought in 3 units of SPMTs. 24 axle lines each, 72 axle lines total, under the bridge. They erected gantry girders and megajack 500 towers on top of the SPMTs. Lifted the bridge off, walked it 300 meters. Across the confined site, over the river. Dropped it onto 2 abutments at 2 different heights, using the hydraulics to absorb every centimeter of the mismatch. They did not miss. If you think a 1,000-ton bridge is impressive, let me show you what these things can actually do. May 2024, Brownsville, Texas, a shipyard. They needed to move an offshore wind installation vessel called the Charybdis, not the bridge over the river, the actual ship. 880 axle lines of Scheuerle SPMTs. Underneath one structure, the total weight, 23,163 tons. The current world record for the heaviest object ever moved on wheels, by any vehicle, anywhere, in all of human history. 1,100 tons in Leverkusen was a single bridge section. 23,000 is a 30-meter-tall, 320-foot-long full ship rolled across a shipyard on tires. Slowly, carefully, without breaking it. And one more, because if the Charybdis is the absolute record, the Johan Sverdrup is the most beautifully engineered. The Johan Sverdrup oil field, Norway. They needed to move what's called a main support frame, the structural steel skeleton that holds an entire offshore platform together. 16,258 tons, with grillage, 604 axle lines of SPMT underneath it. The thing is so big that when it's being moved, it has to be raised and lowered hydraulically as it rolls, to clear obstacles its own engineers couldn't see around. 604 computers all talking to each other, keeping 1,000 wheels in perfect synchronization, holding a steel cathedral level, while the ground beneath them is anything but. Here is what all of this does to the numbers. Worker safety. Crews are off the live highway, off the water, on solid ground, in a staging yard. No traffic exposure, no fall risk, no shared workspace with drivers running 80 miles an hour. Motorist disruption. Months becomes hours, and the structure itself. Prefabricated bridges built off-site are better bridges. Controlled conditions, better concrete cures, tighter tolerances. It's just a better product. Imagine standing under that highway. 3 in the morning. The road above you is dark, empty, closed for the weekend. There's nothing to hear except a low diesel hum from a power pack unit a few hundred meters away, and a quiet hiss of hydraulic oil moving through hoses. The bridge above you is moving. You can't tell at first, but over the course of an hour, the deck has slid sideways by maybe 30 feet. The crew is on radios, whispering. The lead operator has a joystick, inputs the size of a fingernail. The bridge weighs more than a destroyer, and it's gliding past you at about the speed of a slow walk. By Monday morning, that bridge will look like it's been there for 50 years. The road won't even know it changed. The big story is the story nobody wrote. Sometime in the 2000s, civil engineering stopped treating infrastructure as permanent, started treating it as modular, as replaceable, as movable. Ships don't have to be new to be longer. Bridges don't have to die where they were born. And the bill for all of it comes in weekends, not decades. Last thing, because we're not even done with this technology yet. Mammoet, the same Dutch company that co-invented the SPMT in 1983, has now built a fully electric SPMT. Battery-powered, zero emissions, same wheel architecture, same hydraulic compensation, same modular coupling. They completed their first major all-electric heavy transport job recently. The next generation of mega moves is going to be silent. No diesel, no fumes, no engine roar at 3 in the morning when they're walking a bridge across your highway. Just 600 quiet electric motors, carrying 20,000 tons of steel through your sleeping city. Modular movement is leaving the bridge and ship industry. It's spreading. Small modular nuclear reactors, built in factories, then trucked to power plant sites, walked into place by SPMTs, modular space stations, the new Axiom station that will replace parts of the ISS, built-in modules on the ground, lifted as units, connected in orbit, modular semiconductor fabs, $2 billion facilities, assembled off-site from prefabricated clean room blocks. Once you understand the principle, you start seeing it everywhere. Build it elsewhere. Move it whole. Don't disrupt the running system. The factory has left the construction site, and the construction site has become a delivery dock. A 1,000-foot ship gets longer. A 1,000-ton bridge walks across a river. A 50-year-old highway corridor gets a brand new span between Friday night and Monday morning. None of this was possible 40 years ago. All of it is routine now. Next time you're stuck in traffic, look up. There's a good chance the bridge you're driving under didn't used to be there.